It's crazy to me how much time I spend setting up, and taking down, setting up, and taking down, setting up, and taking down. I just realized I didn't tell my last class a joke today. Oh, and nobody said anything. I can't believe it. I wonder what was the joke. I didn't tell the joke. Those poor people. How will they get through the day?
And do? You do math jokes or just regular?
Okay, folks, I heard a dip in volume. I think that means that you're just about done. No, you all stopped talking. I swear it went silent. You're still talking, I'll let it be. Gabe, that was good. Hector's. You're Omar. Okay, that's what I thought. Hector's not here. No, you're Hector. Yes, you're Hector. Okay, there we go. Hector, Valeria, Ellen. There's no Ellen. No Ellen. And Emily. And then Anya. I'm going to put your name on the list. I'll always have an attendance sheet in the back.
Just so everyone knows, I am trying to learn your name as well. If I mess up or if I don't know your name, please forgive me.
Yeah. Okay, folks. Let's come back together as a group here. Now, first of all, just to clarify, my attendance sheet is always going to be sitting all the way in the back, so when you come in, you can sign in. So just to be clear, Hector, you are here. Yes. And you were on time. Yes. And Valeria, you're here.
Yes.
You were on time.
Sorry.
No, it's okay. And we don't have an Ellen, I don't think. But everyone, just so you can all meet Anya. He wasn't in our first class on Monday, but he's here now. So now this is our group. Let's see, 1, 2, 3, 4, 6, 7. Yeah, there's 7 of us. A nice round number. Okay, so let's review. I always like volunteers, but otherwise I'll just call on each of you. Because I mean, there's only 7 of you. I can probably call on everybody for something. So who'd like to cover rational? What is a rational number? Volunteer first, Emily.
It's a number that we can put into a fraction and then terminate.
Okay, you've got a good chunk of it there. A rational number is a fraction, so it'd be like 1/3 or -2/5. And what terminates?
Once you simplify it, they repeat.
The fraction terminates? Or the
decimal.
Decimal. The decimal terminates, correct. So if you have, say, 1/2, it terminates as 0.5. If you have 1/3, it repeats as 0.33333333. So yeah, rational numbers can be written as fractions of whole number over whole number, and the decimals stop or repeat. So perfect. Thank you, Emily. Who wants to do irrational? Gabe, go for it.
Irrational is going to be not fractional.
Yep, non-fractional, such as?
And like pi.
Yeah, pi is a good one. That decimal, what do you know about that decimal?
So it doesn't terminate, but it doesn't repeat as well.
Exactly. So an irrational number cannot be written as a fraction, and the decimal keeps going and going and going forever with no repetition.
I had a quick question. So yesterday when we did the rational set, does not include and have the fraction -3.2 over 5. It's because it's a
right, because that was a decimal.
Okay. I just
Now,
wanted to double check.
good question, Gabe. What did I say? 3.2 over 5.8?
Yeah, the -3.2.
Yeah, so this isn't technically a rational number. It's not written as a rational number yet, because it has to be an integer over an integer. So what you could do is just multiply the top and bottom by 10, and then you would get 32 over 58, and now that is written properly. Okay, so to be written properly as a rational number, it should be an integer over an integer.
So 3.2 over 5.8 would be irrational at that point?
No, it's still rational.
Okay.
It's just not written in a way that it's obvious. Right, kind of like looking at 0.33333. It's a repeating decimal, therefore we can infer that it's rational. But the core definition of rational is integer over integer. Yeah. Okay, really good questions, Gabe. Okay, so there we go. What is interval notation? I'd like to cover that one. What is interval notation? Valeria.
You said the lazy person number line?
Yeah, the lazy person's number line. So let's just look. If I wanted to say something like, I'm thinking of a number between 1 and 10, I could write it like that with inequalities. If I want to turn that into a number line, I would put 1 and 10 on it. I'd use closed circles because it could be equal to them, and I would shade everything in between. Now, no mathematician wants to write a number line when they don't have to, because it's so much easier just to include the numbers 1 and 10, and then have a symbol, in this case a bracket represents a closed circle, and now it's very nice and simple. So I call this the lazy person's number line because it has the same information as the number line. In fact, sometimes in some textbooks, you'll even see them do this. Instead of a closed circle or an open circle, they'll actually use a bracket. Now, isn't that nice and consistent? Like, then it's literally using the same symbol that you'd use for interval notation. Now, more importantly, this might seem lazy. It's actually not just lazy. You could not type this into an email. Right? You can't type a number line into an email. You'd have to like copy paste a picture and attach the picture. Whereas this, you can just type bracket 1, comma 10, bracket, and it's something you can type. So it's lazy, and it's also for the 20th century. Like, it's easy to write it via an electronic means. Okay, great. So that's interval notation. When using interval notation, what symbols do you use to mean included? So what are all of the included symbols? You can tell them all to me. Who'd like to do this? No pressure, Omar, Nadine, and Anyang. Yes, go ahead, Omar.
Included would be a bracket.
Yeah, included means a bracket.
And then greater than or equal to?
Greater than or equal to, less than or equal to. And what kind of circle?
It's a closed circle.
Yeah, closed circle. So all those symbols go together. Those are your inequality symbols for included. A closed circle means included, and a bracket means included. What are the symbols for not included? What are those symbols, lady?
Parentheses,
Yeah?
and then less than, and then greater than, and then open circle.
Yeah, very good, an open circle. Now, Anyang, we're reviewing what we did on Monday, so this might not be a very good refresher for you because we're doing it so quickly. But we are about to do problems with this. So keep watching, and we'll do some good problems for you. Okay, now where does infinity go? Where does infinity go? Does it go with the included or the not included? Not included, because you can't actually get to infinity. Okay, well, wonderful. So those are all of our symbols. That's what interval notation is. And then finally, I don't know if we did this together. How do you type infinity into more? Did we do any more questions?
Yes, sir.
Oh, we did? How do you do infinity? Yeah, just oh. Yeah, the letters, not the numbers. Yeah, yeah, there we go. Okay, well, those are my warm-up questions. It's just a review of the main ideas that we did last time. I tell you what, so we did do some problems and more.
Yeah,
Did we actually type some in?
Yes.
Okay, good. All right, so there's more. Here we go. Where are we today? Today is January 16th. We will cover section 1.2 and 1.3. And then Monday, we're not coming into school because it's a holiday. If you'd like to, I'll still be here in the room with the lights out, just sitting here. So if you want to come in, we could do class. Anyone? No? I'm just kidding. I'm going to be home. Okay, so yeah, no school on Monday, but even though we're not meeting here on Monday, your homework is still due. So you still have to complete all of your more homework by Monday. Now you might say, Mr. G, that's not fair. I don't want to do homework on a holiday. You don't have to. You don't have to do it on Monday. You can do it on Sunday, Saturday, Friday, or tomorrow, Thursday. So you have plenty of days in front of you to do your homework so that you don't have to do anything at all on Monday. You can just sit around and relax. Okay. I'd like to go ahead and review the syllabus quiz, and then don't forget to tell me to tell you a joke. Because in the last class we did the syllabus quiz and I forgot to tell a joke. Well, let's do the syllabus quiz. Everybody have it out with them? Okay. If you've got it all filled out, great. If you have a couple blanks, that's okay. You can fill them in as we go. So I'll just go around the room asking questions. We will start with Hector. Hector, at the top. I need to bring a what? Calculator. Yes, your graphing calculator to class every day. By the first week of class, I need to log on to what website? David? More. Very good. The packet. Okay, so every note packet, which you all now have a note packet, this is what we started filling out. Every note packet is worth 20 points, and I will lose what for every problem that I leave blank or incompletely solved? Omar? 1 point. Yeah, 1 point. Now, that might not seem like a lot. Like, if you just leave one problem blank, you only lose a point, you get 19 out of 20. That's still pretty good. But I've seen people turn in packets where they have like half the packet blank, and the packet has like 50 problems. So you could easily fill out more than half of the packet and yet get 0 points. So I really want to encourage you all, always fill out the entire packet. Okay, the practice test. The practice test is worth 20 points, and you'll lose what for every problem left blank? Any? Yeah, 1 point as well. So do the whole thing. The video assignments. I'll watch the videos when? Yeah, before class. Always before class. You'll feel more confident and more prepared if you watch the videos before you come to class. Okay, and the more practice assignments, always do on the what? It's a day of the week. Always do on the Monday after the lesson was taught. So this week we're doing lessons 1.0, 1.1, 1.2, 1.3. All those are due on the following Monday, which is this upcoming Monday. Okay, and now, oh, I have blank late passes I can use to extend an assignment by 1 week. How many late passes did I give you? Oh, I guess in the syllabus I said 5. Online I actually gave you 10. So I gave you 10 late passes. So if you're running up against the due date, it's almost midnight, you're really tired, you can click late pass and then it'll extend it by a week and then you can finish it at your leisure. The thing is, once it goes past the due date, you can no longer click the late pass option. It's just late. So then you'd have to email me and say, Mr. G, will you please open it back up again? And then I'll go open it back up again. So it'd be much more handy if you just click the late pass before it's due. Okay, test. If I'm not in class on the day of the test, I will receive a what on the test? A 0. However, if I am going to be absent on the day of the test, you have how many opportunities to take the test at the testing center? 1, right? So all of you get 1 freebie where if you're not going to make it to class on the day of the test because your car broke down and you have to go pick up your kids or who knows what, then you email me, say, Mr. G, I'm not going to make it to the test. And I'll put the test at the testing center, which is downstairs, and then you can go take the test within the next 3 calendar days. But that's only a one-time shot. You have to be here on a regular basis to take your tests. Okay, final exam. I will keep all of my what, Hector?
Chapter tests and
yeah, just keep all of your tests so you can study them before the final. Okay, attendance. I will sign in and be in my seat at the start of class, which is at what time? 12:30. I'm allowed up to 2 tardies for free, but starting with the 3rd tardy, I'll lose what from your final grade? Gabe? 5. Yeah, 5 points. Now, technically, 5 points, just so you know, on the final exam is 2.5%. 2.5%. So if you had 1 more tardy than you should have, your 100% will go down to a 97.5. So 2.5% might not sound like all that much. You're like, hey, I can be tardy a couple times. It's fine.
that's assuming you get everything you would make. This is when you get everything good.
Right. Well, I'm just saying, in perspective, if a tardy is worth 2.5%, then you could be tardy 4 more times than you should be and only lose 10% off your final. If that's worth it to you, being late and all. So it doesn't immediately kill your grade. It's just slowly suffocating. So again, I hope that you're not tardy. Okay, same thing goes for absences. Starting with the 3rd absence, you lose 5 points from your final grade, which is 2.5%. Okay, I can be absent a maximum of 5 times, excused or unexcused. But on your 6th absence, you must meet with Mr. G during office hours to discuss your progress. Otherwise, you'll be withdrawn. So here's the thing. From time to time, I know this won't be any of you. None of you will do this. But every once in a while, I have someone who's absent. All of a sudden, there are 6 absences. And I'm like, where is this person? Are they ever coming back? So I need communication to understand what's happening. Because sometimes people have a valid reason for being absent 6 times. It's not often. Normally it's an invalid reason. They're just missing class. But sometimes you have a valid reason. If you have a valid reason, if you can get your game back together and bring up your grade, then you can stay in the class. But if someone doesn't even write me back, they never even talk to me, and they're just absent, I assume they're MIA. What is that, MIA? Missing in action. Where did that person go? I have no idea. Okay, so I can earn extra credit for perfect attendance. If you have 0 tardies, you earn 5 bonus points on the final exam. And if you have 0 absences, you earn 5 more bonus points on the final exam. Okay, Anyang, by the way, all of these answers are in the syllabus. So you can also go back and look at the syllabus. Okay, before the day of what, I will come into office hours for a 5-10 minute chat to review my notes and homework. Before the day of first exam. Yeah, so you have a couple weeks. If not, you'll lose what from your first test grade? 50%, which is a big threat that I've never had to do to anybody because everybody just comes into my office hours. And I have office hours right before this class. In fact, Emily came in. No, not yet. Okay, but yeah, before coming to this class, just go to my office. I'll be there. You can talk to me, and then we can come to class together. Okay, if I earn less than what on any test? 70%. 70% is the cutoff. If you earn less than 70%, Mr. G will report my grade as a 0 in the grade book, not permanently, just until you come into office hours to review the test. And then after reviewing, I'll enter your grade. Here's the thing. You do have to come in to review your test because that's going to help you learn the material and prepare for your final exam. If you never come in, I leave to 0. Because that's what it says in the syllabus. I leave to 0 until you come in to review your test. Okay. Yes, Gabe?
I have a quick question for the syllabus. For the email, I totally forgot. Is it our personal email or through Canvas?
I would prefer you email me at my school email, not Canvas. But if you send it in Canvas, that's fine. I'll get it out of
Okay,
there.
so I can do it from my personal email?
I would prefer your personal.
Okay, 'cause I wasn't sure which one, so I figured it out.
Yeah, personal email is better.
I didn't know my personal email, but if my school email is linked to my personal.
Yeah, that's fine. It can be personal or school email. Okay. Anya, do you have any questions right now?
No.
Okay. I know that was a lot all at once because we talked about all this stuff on the first day. You what?
I would review it.
Wait, what did you
I would
say?
review it. I would study it.
And he said he's gonna review it.
Okay, good. Yeah, and then ask me any questions and email me. All right. Well, there we go, folks. So that's the little syllabus quiz. How about during our 10-minute break, you can just bring it up here and set it on the desk, and I'll collect it. All right. I did not forget to tell you a joke. So, Anya, first of all, you didn't get to hear the joke from yesterday, so I'll say it again. What did the pirate say when he turned to 80? Aye, matey. All right, well, anyway. Okay, so now, here's this one. Where does the general keep his armies? Wait for it. Where does the general keep his armies? In his sleeveys. His armies
Oh my god.
are in his sleeveys. Yeah, it's a very silly joke for children, but I love it. I think it's a wonderful joke.
Once you become a dad, you're gonna learn a lot of it.
Yeah, exactly. And my daughter, she's 2.5. I taught her this joke because she's so funny. She says it like this: where does the general keep his armies? She says, in his sleeves. And I'm like, honey, that's even funnier. All right, so here we go, folks. Here we go. This is where we left off. I think we finished talking about this. Did we? Did we finish talking about all that? And I think we moved on and we were about to do practice problems.
Yeah.
Okay. So, Anyang, this is for you, but this is also for everyone. Let's review some of these practice problems. How many did we do together? Just the first two? Okay, so then let's start with the third problem, which is 2 to 7. I'm going to write it in the order that you have it. So I've got a number line going from 2 to 7. And it's shaded in between. And we need to fill in the interval notation as well as the inequality. So the interval notation is pretty straightforward. You just take the numbers, 2 and 7. And what symbol do I use for an open circle? A parenthesis. And what symbol do I use for a bracket? For a closed circle? A bracket. Okay, so that's interval notation. What this means, remember, we're talking about what numbers are in your set. So the numbers I have in my set are everything between 2 and 7, but not 2. So those are the numbers that I'm saying are valid. And then to write that as an inequality, we just put x in between 2 and 7, and we say x is what? Greater than, strictly greater than 2, because it can't be equal to 2. But it's what to 7? Less than or equal to. Yeah. So that's how we would express this number line as an interval and as an inequality. So, yeah, so what are we saying? We're responding to the question, what numbers are we considering valid solutions to this problem? So for instance, maybe this is the set of values that you'd be willing to spend for a coffee at Starbucks, right? Depending on the drink, you're like, hey, the most I'm gonna pay is $7. There's no way I can even rationalize spending more than $7 on a coffee.
Wait.
What?
It's your budget.
Right, yeah, it's too much. And on the other hand, you're like, I will not drink anything that only costs $2. That's not high quality enough. I need it to be more than $2, but less than or equal to 7. And so you're saying any dollar value between there, I'll buy the coffee. Right, so that's what you're saying. So there's lots of solutions, right? How many numbers are there between 2 and 7? How many numbers are there between 2 and 7?
So
How many? More than whole numbers. You've got 2.5 in there, you've got 3.1 in there, you've got 6.852 in there. How many numbers are there? How many are there? A lot. How many is a lot? Infinitely many. Yeah, so when we talk about a solution like this, there's actually infinitely many numbers in there. You've got infinitely many numbers that are part of your solution set. Yes, Gabe?
it's really infinite. You can't like.
It's really infinite. Yeah.
2.576.
Oh, yes, yeah.
Just go
So you
on.
can just keep on doing more and more digits.
Because you can cut it in half, right? You can cut that in half, and you can cut that in half.
Yeah.
Never stops.
Okay, well, good. Well, I'm glad we talked about this. So all three of these
Multiplying zeros.
Yeah. are just ways of saying what numbers you're considering part of your solution set. Okay, so let's try the next one. The next one says that it's -5 to x to 0. Well, look at the structure of this problem. Isn't the structure of this problem the exact same? I mean, we're literally just swapping out the numbers 5 and 0 for 2 and 7. So let's not even, I won't even bother doing this one. Let's go to the next one. So this is -3 to 3. That's our interval. We're looking at all the numbers between -3 and 3, but not actually -3 and 3. So what circle do I use on the -3 and 3? Both open, and we're considering everything in between. And then as far as an inequality goes, again, you put the x in between the -3 and the 3, and what type of symbol do you use? Less than or less than or equal to? Strictly less than. Now, by the way, folks, notice that the symbols are always opening to the right. Right? They're always opening to the right. One mistake I saw the other day was that every once in a while people were doing something like maybe this. But that doesn't work. That doesn't show that x is between those two numbers. It has to be less than less than. Just so we're clear on how you write an interval. It's always less than less than. Okay, the next one was between 5 and 7. So they're telling us it's a closed circle at 5 and a closed circle at 7. And so we want to consider all the numbers between 5 and 7, including the numbers 5 and 7. So how do we write that in interval notation? Yeah, this would be brackets. Now, Anya, just to fill you in, see, this is why we said all these symbols go together. So if you're saying that you are including the number 5 and 7, you'd use a closed circle on the number line to say you are allowed to choose the number 5, and use a bracket on the number 5 to say you are allowed to choose the number 5. And then for this, you'd say x is between 5 and 7, and use less than or equal to say that you could be equal to 5. So these symbols all mean including, as in I'm thinking of a number between 5 and 7, including 5 and including 7. Is that okay?
Yeah.
Okay. Have you seen this before? Yeah. Yeah, it's okay if you haven't. Okay. All right, well, there's that, folks. This next one is a little tricky. X is less than or equal to 3. Where do we even go from there? Because there's only one x. Right. And so my answer to you is when you're not sure how to approach a problem, what's the best thing to do? Right, for sure we'll have a 3. The answer is draw a picture. So always, always, always when you're confused, you're like, what do I do? I've never seen a problem like this. Draw a picture first. So we know it's a 3. What kind of circle is it? Closed circle. And which way do we shade left or right? This x is less than. Less than. Yeah, less than is left, greater than is right. Right, so we need to put the negative infinity number right there so that we can see it, so we know what to put on our interval. Very important to always put negative infinity on your number line so that you're reminded, oh yes, my interval is from negative infinity to 3. So, Anya, what symbol does the 3 get? A bracket or a parenthesis? And you can check right here. We're talking about a closed circle, so it's a, that's called a bracket. Yeah, yeah. So this is a bracket because it's, let me make it slightly better. It's a right-angled mark. Yeah. And then a parenthesis is curved. So that's bracket. There we go. And then these are parentheses. Okay. So yes, this will be a bracket. And then infinity always gets a parenthesis because we never get that. Okay. How's everybody feeling about all this? Lee?
If you don't mind me saying, when I first handled this myself, I was really confused. A lot of people, they said, look at the alligator. I didn't like the alligator. The way I looked at it was an arrow, like Cowboys Indians. So depending on which way the arrow is depending on how you can actually tell on the number line which way it goes and whether or not it's greater than or less than.
Yeah, so in this case, the arrow is technically pointing towards the left. And that rule works provided that x is on the left.
Absolutely.
X does have to be on the left in order to use that rule of the arrow pointing.
Yes.
Okay, great. So then this next one, the infinity 9, we all agreed this is a typo because you cannot have a number line with infinity on the left and 9 on the right. Because that just doesn't work. Infinity, that would have to be a negative infinity. So either this problem was supposed to be negative infinity 9, or what was the other possibility? Or they meant to switch that, and the problem was 9 to infinity. We could do either of those problems. We could do both of those problems. So let's all just choose. Should we just do the negative infinity to 9? Although we did just do that one with the 3. Let's do the other one. Let's do 9 to infinity, just so we do something different. There, 9 to infinity. So our number line, we go from 9 up to infinity. Is it a open circle or a closed circle? Open circle, shade to the right. And now we just do the inequality. So this is, we have an x, a 9. Remember, x is always on the left. So what symbol goes there? We're shading to the right. So is it greater than or less than? Greater. That's it. Yeah. Okay. Everybody, you can go ahead and try the next one. In fact, you can do the next 2. If you haven't already done so, go ahead and do the next 2. And then I'm done, just so you know. We're doing all these guys with you, so you can be filling it in like here. If you prefer to write on line paper, I understand what you're talking about. But my preference is that you're taking the notes right on here. And that way I can collect this on the day of the test.
No typo with the.
What? This one was a typo.
Yeah.
I think this one's correct. This one's correct. Yeah.
What was changing the name? This one I don't have that.
Oh, well, you know what's interesting? Hector, thank you, Hector. Hector points out a good point. There's more than just 2 interpretations. It could have been that they meant to do 9 to infinity. Right? So what did they write down? This is fun. They wrote down infinity to 9, which is impossible. So they could have meant 9 to infinity. Or they could have meant negative infinity to 9. What else could they have? They could have meant negative infinity to negative 9, which would have been a super typo. Or they could have even meant negative 9 to infinity. All 4 of those are possible. All 4 of those are possible, but this one's not possible. Okay.
So which one do you want to do?
We did this one right now.
Okay.
Yeah. Okay, so I'm just checking everybody else and work on those last 2. Check it over.
Oh, there.
Very good.
I did a little, I didn't do this. But this is really good. Oh, sure, you're right. You're right. I did last
Part of
night.
the inequality, and inequality always has to have a big descendant. So we're not saying 9 is greater than infinity, because that's blatantly false. 9 is not bigger than infinity. We want to say x is greater than 9. So erase both of those.
Okay.
And let's, oh, and see, I have it up there on the board. X is greater than 9, is what we're saying. So go and write x is greater than 9. Because we're talking about a relationship between x and the number. There you go. That would be x is greater than 4.
Yes.
Okay, yeah, you. Okay, so just so everyone can check their answers, and then we'll move on to the 4. The infinity right there, so that's 4 to infinity, which is x is greater than 4. And then the last one is x is greater than or x minus 3. So my number line at 8. That is. Okay, so check your work. And we're not done. We still have a couple more practice problems to do. Anyone have any questions about these before we get going? Okay, so the next couple problems we're going to do are a little more fun and challenging. They're a little different. Plus, we're going to get the left or right problems. So let's take a look here. I'm going to.
The ones where you need a U for your answer?
Yes, the ones where you'll need a U for your answer. So I'm going to come over here, and let's do number 9 first. So number 9, we've got this set of numbers, x, such that x has to be less than or equal to -1, or we want x to be greater than or equal to 1. So what's the first thing we should do? Draw a picture. So we're going to draw our picture here, and we'll say, well, compared to -1, we want x to be less than or equal to it. So it's a closed circle, and we shade left. How's that so far? Or we're going to compare x to 1. So I put a 1. And I want it to be greater than or equal to. So it's closed or open. Closed, and we go greater, so to the right. This is going on to the left, negative infinity. This is going on to the right, positive infinity. And that tells us our intervals. So what's our first interval, Omar?
It's negative 30.
Yeah,
Negative 1 in the bracket.
for the bracket. Union, what's our second interval, Nadine?
Yeah,
One with the bracket?
and
Yeah, very good. So that's our interval notation. And again, that's something you could write down in an email to somebody fairly easily. And then they would know you're thinking of all the numbers in the world, less than -1 or greater than 1, including -1. 10, you can do on your own. So I'm going to let you all do number 10 on your own. Let's go and do 11. So number 11 is a little different. They're saying curly bracket means a set of all numbers in the universe such that, that vertical line means such that, x has to be less than or equal to 5, or quite simply, equal to 6. Okay, so we draw a picture. What do we draw for the x is less than or equal to 5? Yeah, close circle on the 5, and we shade to the left or right. Now what do we draw for the x equals 6? Yeah, what kind of dot? What kind of circle? A shaded circle. Remember, shaded means truth. And we are definitely saying that x could be 6, so we just put a shaded dot on 6. Now how do we write this as an interval notation? Well, the first interval is pretty straightforward. We've done these, so that's going from -infinity to 5, the bracket. Union, is this an interval? It's just a single point. Something to keep in mind, all of these intervals, how many numbers do they contain within them? I'm sorry, how many total numbers on the interval? Infinitely many. There are infinitely many numbers in this interval right here. Because all these numbers right here, you have infinitely many numbers that you're including in your set. An interval is used to demonstrate infinitely many choices. Whereas that's just one choice. It's just a single number. So instead of an interval, we'll just use set brackets to just say the number 6.
just the thought,
Yeah, just a shaded circle means you're just talking about that number.
what you said,
A closed circle?
what you said, truth,
Oh, wait, shading means truth.
just truth.
Shading means truth. It means it's truth as part of your solution set. It's truth as part of the numbers you're considering. So, like when we shade this, we're saying all these numbers are possible solutions. And when we put a closed circle on 3, we're saying 3 is a possible solution. And when we put an open circle on 4, we're saying 4 is not a possible solution. But everywhere you shade it is a possible solution. So shading means possible solution, shading means possible truth. All right. Now let's try 2 of the next ones here. We'll just do 2 of them. Number 6. We want the set of all numbers such that x just isn't equal to 5. That's an interesting statement. You can choose any number in the universe except 5. So what would that number look like? That is a very good guess, and that is correct. You're saying you can choose any number in the universe except 5. And that's what the number line is. We just shaded every number in the universe except for the number 5. So then that's 2 intervals. So what, Hector, what's my interval on the left?
On that, I'm sorry, I'm just drawing my right now.
-infinity to 5, and then union. What's the interval on the right?
1,035.
Well, we always read left to right. So it'd be 5. There. Yeah. So that would be your union for that set. Yep.
For 10 with the lines like over that.
Let's look at that one. Number 10. Gosh, maybe I shouldn't have skipped number 10. It says x is less than 3 or x is greater than or equal to 2. Oh, that's kind of funny. I mean, if you're less than 3, you're shading this way. But if you're greater than or equal to 2, you're shading this way. And so technically, if I keep shading, what have I shaded? Everything. So I mean, technically, any number. Yeah, good point. That was a tricky one. Any number is going to be either less than 3 or greater than or equal to 2. Choose any number, and it's going to make one of those true. And that's what or means. It just has to make one of them true. So in fact, what's our interval now? Yeah, negative infinity to infinity. Oh, well, that was a fun one. I'm glad you asked about it.
I do have a question about the level 1.
Yeah.
What was the answer that was
So the interval on the left is negative infinity to 5 with a bracket. And then you're unioning with it just the number 6. And when you just want to say a single number or just a couple of finite numbers, you use the curly brackets. The curly brackets means set notation. It means you're building a set of objects. Okay, so there was just one last, or number 7. Let's do that one together. Now we're saying, I want all the numbers in the world such that x just isn't equal to negative 3 or 4. So what would that drawing look like? Yeah, very similar. You're not including negative 3. You're not including 4. But you are including everything else. All the way to negative infinity and all the way to positive infinity. So how many intervals are there? 3 intervals. So we'll use the union symbol twice. What's this interval over here, by the way? And what's this interval in the middle, Anya? That's a negative 3. So this interval is going to go from negative 3 to 4. So we would write down negative 3 to 4. And then since it's an open circle, what would we use, a parenthesis or a bracket? Yeah, parenthesis. So there's that interval right there. And then this last interval over on the right-hand side, maybe? Okay. Well, folks, that's interval notation. Again, interval notation is the lazy person's number lines. It's how you would type solutions to a friend via email. And it's a description of all the numbers you're saying are possible solutions. And that's interval notation. Emily?
For number 8, since it says plus and negative.
Plus or minus, yeah.
Is a negative 1.
Correct. So on number 8, we're saying x just can't equal 0 or plus or minus 4. That's 2 different numbers. So you have negative 4, you have 0, you have positive 4. You're not including any of those, but you are including everything else. So how many intervals are there this time?
4.
Yeah, 4 intervals. From negative infinity all the way to positive infinity. So you have this interval, and then this interval, then this interval, and then this interval. Okay, I'll skip over on a second, finish writing that down.
I just asked the shading.
Yeah.
Between
Yeah, you should have. Yeah. Well, I encourage you to write everything down. Like no matter what, it is that no, like right now, like while we're in class, right now, write down as much as you can. Because sometimes just the process of writing gives you the other stuff. By doing it, you understand it better. So I would go ahead and write these down. Like the one that we just did there, do number 8 with me right now. They're saying all the numbers except 0 plus or minus supposed to draw a number 1. And you'll put the numbers negative 4, 0, and 4. And make a suggestion. Okay. So when you make your number line, first thing you want to do is just put in the numbers. You just put in your numbers. And we're going to layer the information in. So first we put in the number 4, 0, and so 0. Now go and you can put infinity. Then go back and say, okay, well, what symbol are we going to close circle or open circle? Because we're not including the numbers. It's not including. Yeah, open circle. So put an open circle on all 3 of these. Yeah, right there. So that one's there you go. Very good. Okay, so now we're saying don't shade those 3, but shade everything else. So you can shade that, keep that. So we're saying those are all the possible numbers that will work. So now we look at this and there's an arrow. Because it keeps going up to infinity and back to negative. So now each of those chunks of shading is an interval. So that interval, all the words for that. So you have one interval from negative infinity to negative 4. Another interval from negative 4 to 0. Another interval from 0 to 4. Another interval from 4 to 0. So now start writing those intervals down. This is simple because all of these are going to use parentheses. So do parentheses, negative infinity to negative 4 parentheses. So what are shade? So negative infinity to 4. Yeah, negative. Comment. In between the numbers. Because we're separating them apart. There we go, parentheses. And then the letter U. You can go to 4. So now 4 this interval, so from negative 4 to 0. So another parenthesis. Get parenthesis. The other way around. Because we're capturing the information as negative 4 to 0. So parentheses. There are negative 4, comma 0. There parentheses. Now we've run out of space. We still need to keep writing. So what do you do? We'll go on to the next line. So now we're going to do this interval. So parenthesis, 0, comma 4, parenthesis. This one's positive. And then finally, this last interval, so another U. And parenthesis, 4, comma 3. Okay, so that would be the whole answer, but we try to get all that on one line. So that we don't run out of space. So you can start with it. And by the way, your infinity, I would look on your infinity because this looks like an 8 cup. Try to make it sideways as much as possible. Yes, that's better. Okay, folks. Let's go. Oh, here's your pen. Let's go ahead and check out the next section. The next section just talks about coordinate grids. And I do want to say a couple things about a coordinate grid. First of all, I had a YouTube video for us to watch, but the sound in the room is not working, so we can't watch it. But I'll still talk to you about the person. So up at the top it says the Cartesian coordinate plane is named after who? Does anyone know who the Cartesian coordinate plane is named after? You can probably take a guess. Yeah, a guy named Cartesian, right? Or Cartes anyway. And that's actually very close to the truth. The person's name was Rene Descartes. And perhaps you've heard of Descartes. He's a philosopher. And you can see right there at the end of his name, Cartes. So his name is Rene Descartes. And he popularized the use of an XY axis in the 1500s. So he didn't invent the XY axis. People before him had used it, but it wasn't very popular yet. And so he wrote a book and it popularized it, and now everybody uses it. So he did create this invention of the XY axis, the coordinate grid. So that's one notable fact about him. He was alive in the 1500s. He was a philosopher and a mathematician. And as a mathematician, as I said, he popularized the use of the XY coordinate grid. And as a philosopher, he is famous for the phrase cogito ergo sum. Has anyone heard cogito ergo sum? It is in popular culture, so you might see it in movies or TV shows. Cogito ergo sum means I think, therefore I am. Yeah, or
So before you popularized it, why did people use coordinates?
they didn't really graph things. They did it in other ways. Yeah. It's a good question, actually. I mean, math is a technology that only goes back so far. So, I mean, before they had it, they weren't doing it. Yeah. All right, so that's Descartes, and as I said, it's named after the Cartes part of his name. So the Cartesian coordinate grid, I think we've all dealt with coordinates before. Any given coordinate on the grid is given by x comma y, right? It goes in alphabetical order. Another way of writing it is that the x is the right-left information, and the y is the up-down information. I oftentimes write RL for right-left, and UD for up-down. So a coordinate is giving you the right-left information, followed by the up-down information, and that's a coordinate. Yep. One thing that we'll just look at the grid here. We do number the quadrants. So like this quadrant over here is called quadrant 1, and then over here is quadrant 2, down here is quadrant 3, down here is quadrant 4. It's just a nomenclature, a labeling, it's vocabulary. And gosh, they say some facts there. The origin is at 0.00. Anyway, that's pretty much it. I just wanted to point it out to you. We will use the graph over and over and over. We're going to do a lot of graphing in this class. So that's all I have to say about that. It's a graph. It was named after Rene Descartes, and we'll use it quite a bit. Let's go ahead and keep going.
I have a quick question.
Yeah.
Video,
They're going to fix the volume in this room, and then we can watch it together. Yeah, I'll show you guys next time. Okay, screw page. It'll be our first application of using the coordinate grid, and that is using the distance formula and the midpoint formula. Have you folks seen the distance formula and the midpoint formula before? You probably have, either in high school or maybe even another college class. What you might notice when you look at these formulas is that there's a key concept behind both of them. And I'll show you the key concept. You don't have to write it down per se, but I want you to know where those formulas come from. So first of all, and like I said, you don't have to write this down, but if I wanted to, I'm going to be drawing this diagram right here. Basically, they just have a point P and a point Q in space, and they want to find the distance D in between them, and then they're going to show you how they did that. So I'm just going to, well, no, yeah, I'll show it to you. So we have a point P, which is x1, y1. Then we have a point Q, which is x2, y2. And we want to find the distance between them. And so someone had the clever thought to draw a right triangle underneath it. Because if you draw a right triangle, then now all of a sudden we have a shape, and we can calculate things about a shape that we can't necessarily calculate about just a line floating in space. So someone looked at this and they said, hey, I can apply the Pythagorean theorem to this. So the Pythagorean theorem is a squared plus b squared equals c squared, where we're talking about a triangle, a right triangle, whose legs are a, b, and c. So we want to find the distance between 2 points floating in space. We can turn that line into a right triangle, and now all of a sudden we can do the Pythagorean theorem and actually calculate the hypotenuse. So first thing we need to know is how wide is the triangle and how tall is the triangle. So as an example, let's just say that I want to know how wide it is. I know that this x-coordinate is x1, and this x-coordinate here is x2. So how far apart are x1 and x2? What's the distance between them? How would you calculate it? I'll put some numbers in there to make it obvious. How far apart is 3 and 8? How much distance is between 3 and 8? 5. How did you get 5? Oh, you just subtract 8 minus 3. Does everyone feel okay about that? That it's a length of 5? So, yeah, if you're using whole numbers, very simple. And so the way you do that is you do 8 minus 3, which is right minus left. So what's the distance between x1 and x2? x2 minus x1, right minus left. So now we know that the length of this leg is x2 minus x1. Okay, next we want to know how tall is the leg? Well, same thing if I make a vertical line here. Move that over. And I'm starting at my lower y-coordinate, which is y1, and my higher y-coordinate, which is y2. How much distance is there? And again, I'll put concrete numbers in so it makes more sense. Let's say this is a 4, this is a 10. How tall is it from 4 to 10? Maybe 6, because you just subtract, right? 10 minus 4, so the overall length is 6. So you subtract top minus bottom. So in this case, top minus bottom is y2 minus y1. And that's the height of this triangle, y2 minus y1. All right? So far we've done a lot with our triangle. And now all we have to do is do the Pythagorean theorem. And that's where the distance formula came from. So take a look here. I've got a squared plus b squared equals c squared. But I'm going to write it down as c squared equals a squared plus b squared. And so what is my c? The distance. And what is my a? x2 minus x1. I call that x2 minus x1 squared. And then what is my b? y2 minus y1. And now we want to solve for d. D is being squared, so algebraically, how do you get d by itself? You square root both sides. And there's the distance formula. The distance formula is the big square root of x2 minus x1 squared plus y2 minus y1 squared. That is the formula at the top of the page. So what is the distance formula? The Pythagorean theorem. So really write that down. Notice that these formulas are easy concepts in disguise. The distance formula is really the Pythagorean theorem. I'll write that down just in case you're not sure to spell. Pythagorean theorem. There we go. Well, maybe you're saying to yourself, well, Mr. G, I never needed to know that. Maybe, maybe not. You know, it's interesting to see where formulas come from. But the important thing is that by knowing that the distance formula is really just the Pythagorean theorem, you now have two options for calculating a distance. You can calculate the distance between these two coordinates by using the distance formula, or you can just draw them on a graph and do the Pythagorean theorem. That's what we're going to do first. So everyone, let's take a look at number 1. This is our first use of the coordinate grid. We'd like to find the distance between the coordinate 1, 2 and the coordinate negative 3, 5. Very important. These are not intervals. Don't they look just like intervals? They're not intervals. These are coordinates. Coordinates look like intervals, but they're not. These are coordinates. So context tells you we're talking about coordinates now, not intervals. So where are these coordinates? Everyone draw a really good graph in here. So draw a graph. Let's put in the coordinate 1, 2. So it's right 1, up 2. There's our first coordinate. Now, really important, you're all drawing this graph. We want to make a really nice graph. So there's my first coordinate 1, 2. And then my other coordinate is negative 1, 2, 3, left 3, up 5, 1, 2, 3, 4, 5. So here's my other coordinate. And I'd like to find the distance between them. So again, if you want to find the distance, you can do the distance formula. And that's fine. That's what the distance formula is for. You just plug in the numbers and you do a calculation. But we're going to make this into a right triangle. So go ahead and make a little vertical dashed line straight down, a little horizontal line dashed straight across, make a little right angle, and there's your right triangle. Now, from a good picture, you can calculate the height and width of this triangle just by looking at it. So let's look at the width first. The width goes from this tick mark to this tick mark. So how far is that? Well, if you start here, that'd be 1, 2, 3, 4. Now that's okay. So 4 units across. I'm going to label that a 4. Now, how tall is the triangle? You're starting at this tick mark, going up to this tick mark. So how tall is that? 3. So what we have now is a triangle, legs 3 and 4, and we would like to know the distance, d. And so now we just do the Pythagorean theorem. So again, I'm going to write it out as c squared equals a squared plus b squared. You're allowed to write it backwards if you like. And the hypotenuse is our d, the distance that we're interested in. And then a and b can be either of those numbers. It doesn't matter which one you put where for a and b. They're just the two legs of the triangle. So now we have 3 squared plus 4 squared. And so d squared is equal to 9 plus 16, which is 25. And again, d is being squared, so how do you solve for d? You take the square root of both sides, and you end up with d equals 5. So that is the distance between these 2 points, 5. Now let's do the distance formula. Because it's your choice. You might say, well, I like this method. It was pretty simple to do the Pythagorean theorem, and it doesn't look nearly as scary as that distance formula. However, in order to use this method, you do have to make a really good drawing. So the effort you save in not doing that scary-looking formula, you have to put a lot of effort into making a good enough graph that you can count all the numbers off from the graph. Okay, so everyone now, let's do the distance formula. Very careful, this is a best practice. We'll always do this. First, you write the formula as it is. D equals big square root, parenthesis x2 minus x1, parenthesis squared, plus parenthesis y2 minus y1, parenthesis squared. Anytime you're going to write a formula, your first step is to write the formula. This next thing that you're going to do is what I call writing it empty. So what we're going to do is write this whole formula again, just not with the x2, x1, y2, y1. So watch maybe as I do it. It's big square root, parenthesis something minus something squared, plus parenthesis something minus something squared. I call that writing it empty. And what you see there is the structure of the formula. The addition, the subtraction, the squaring, the square rooting. You see all the structure there, but no numbers. So now what do you suppose we're going to do? Yeah, we're going to plug in our numbers. Before you can do that, you have to very carefully label where you want these numbers to go. So this was my x1, y1, and this was my x2, y2. Very careful, make sure you're labeling it that way. Earlier today, I saw someone label it x1, x2, y1, y2. What's wrong about that? It's always xy. Every coordinate is an xy. So it has to be x1, y1, x2, y2. But now we just plug in the numbers. So what's my x2? Yeah, -3. And see, here's what's so great. It's labeled. It's right directly below it. You can literally just go look for the number. x2 is -3. What's x1? 1. What's y2? 5. And what's y1? 2. So you very carefully go in and put in those numbers. We're trying to be as careful as possible because we don't want to just make a typo here. So now we just do the subtraction. Now, if you're comfortable doing things like this, then great, you can do it in your head. But if you feel like you make mistakes with positives and negatives, you should really type this into your calculator to make sure that you're getting it correctly. That means we're going to take a break soon. So what's -3 minus 1? -4. And what's 5 minus 2? Great. Now everyone look real quick because this is super cool. Where did you see the numbers 4 and 3 before? Those are the legs of the triangle. Because remember, the distance formula is the Pythagorean theorem. So now, we finish our computation. 4 squared is 16. 3 squared is 9. 16 and 9 is 25. And the square root of 25 is 5. We get the exact same answer. So the question is just, what method do you like better? Did you like drawing it and doing the Pythagorean theorem directly? Or did you like plugging it into a formula? As far as I'm concerned, if you did this on the test, I'd give you credit either way. Just so long as you show all your steps like this, or you show all your work like this, you can do either of these methods and give them full credit. Okay?
The distance formula
Yeah, that's
is
easy.
easier because the numbers, depending on your numbers, have the size of the number.
Yeah, Hector makes a really good point, folks. As soon as you look at number 2, for instance, I don't know that anyone still wants to make a graph. Because if I try to make a graph of the coordinate 3, -10, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I'm way down there. And then -1, 2, -1, 2. You can still do it. You know, you can make a graph, and then you can count your total height and your total width. It's very possible. If I'm up 2 and down 10, that's a distance of 12. And if I'm right 3 and left 1, that's a distance of 4. So now I can do the Pythagorean theorem. I'm almost done. B squared equals 4 squared plus 12 squared. And now it's just a matter of solving for D. So yeah, I mean, the graph might get bigger. You can still do it. Okay, so I tell you what, folks. Number 2, we already did one good problem of the distance formula. So I'm going to leave number 2 for you to do. Before we take a break, let's just do the midpoint formula now real quick. The midpoint formula. What do you notice about this formula? So that was the Pythagorean theorem. What are you doing in this formula when you add two numbers and divide by 2? Yeah, it is the midpoint. It is the midpoint. Well, that's true. Yeah, like over here it's x2 and x1 squared, whereas over here it's x1 and x2 divided by 2. And that's true, there are certain similarities between the two formulas. Well, let's just look at this formula. What do you call it when you add two numbers and divide by 2? Or what do you call it when you add three numbers and divide by 3? Or add four numbers and divide by 4? What is that process called? Like, let's say you have 4 test scores, and you add all 4 of your test scores together and divide by 4. What do you just calculate?
Average.
Yeah, the average. Median is slightly different. That's the middle value. Well, what's the other word for average? Starts with an M. Mean. The mean, yeah. So it's the mean or the average. So midpoint, go ahead and write down the midpoint formula is just the average. You're just averaging the x coordinates, and you're just averaging the y coordinates. But sometimes the formula looks scary, but the fact is we're just going to average the x coordinates, and we're just going to average the y coordinates, and that gives you the midpoint. So let's do this one. We're going to do number. Well, we could do number. No, I was leaving number 2 for you. Yeah, let's do number 3 as a midpoint. So number 3, we'll do the midpoint. Those coordinates are 1/2, 4, and the coordinate 3/2, -1. Now, I'll always suggest that the first thing you do in any problem is picture. Yeah, graph it. Make a graph. So I'm going to make a quick graph. So how do I plot 1/2? You just kind of put it in the middle. So 1/2, 1, 2, 3, 4. So there's my first coordinate. And then 3/2. What is that as a decimal, 3/2? 3 divided by 2. 1.5. So we're going to go right 1.5. So again, in the middle of 1 and 2, and then down 1. So there are my 2 coordinates, and I'd like the midpoint. So where's the middle of that line segment? Is it like there-ish? Around there, right? So when we're all done doing our work, whatever answer we get better be right around there. Right? Because we're just literally looking for the middle of that line. Okay, so now let's do it. To do the midpoint, you simply average the x coordinates and you average the y coordinates. I'll write down the formula, x1 plus x2, comma y1 plus y2. But I'm just going to strictly add the x coordinates together and divide by 2, and then add the y coordinates together and divide by 2. Because the midpoint is the average. So I've got 1/2 plus 3/2 all over 2. Those are my x coordinates. And then 4 plus -1 all over 2. Those are my y coordinates. We don't really cancel them out. Let's think about it. What's 1/2 plus 3/2 in fractions? You have the same denominator, so 1 plus 3 is 4/2, and 4/2 is really 2. Or you can say 1/2 is 0.5 and 3/2 is 1.5, so 50 cents plus $1.50 is 2. So either way, you get 2. So now let's simplify a little. This is now 2 over 2, and this is now 3 over 2. Right, because 4 minus 1 is 3. And so now 2 over 2 is just 1, and 3/2 as a decimal was 1.5. So that's our midpoint. Is that correct? 1, 1.5. If I go right 1 and go up 1.5, yeah, that's pretty reasonable. There's my midpoint. So there we have it, folks. Those are just 2 nice applications of using the coordinate grid to solve problems, plugging in coordinates like x1 and x2. It's a good question. Sometimes you are supposed to memorize formulas. And for instance, I think you can all memorize the midpoint formula right now. Because what are you doing with your coordinates? You're just averaging them. You add them together and divide by 2. So I think all of you have that formula memorized now. Distance formula, that one's a little more tricky to memorize. How would you memorize a formula like that? Just write it down. 5, 10, 50 times. And you'll have it memorized. I mean, that's where memorization comes from, right? Repetition. So some formulas I'll give you on the test, some formulas I won't. But I tell you what, on the practice test, I'll tell you which formulas you need, and that way you can work on memorizing them if I don't give it to you. All right, well, folks, that brings us up to section 1.2. So that's a good place to take a break. So it's 1:37. Let's come back into the room at 1:47. And class goes to 2:45. Okay. Remember, the only rule for break is you have to leave the room. Even if you come right back in, that's fine. You have to at least stand up and get the blood going. Oh yeah, and I'll take your personal info sheet and your syllabus quiz. You can bring that up here and we'll make a couple stacks. Thanks, David. Right there. Awesome. Yeah, it really does. It's terrible. Yes, I did.
I think I just went up to your camera and went like this.
Oh, very nice. I'm sure that everyone will enjoy that.
You think at the end of the class we can do this?
Yes, absolutely, we will.
Question. Do you think it's possible?
Yeah, what? Yeah. In fact, I think what I'm going to do is I'm going to post them all online. You know what we need to do is get you into my Canvas course.
Yeah, that'd be fun.
Yeah, let's. I don't know how to add you to my Canvas course. There must be a way. I just don't know how to do that. Let's ask Shannon. I bet she knows how to add you to my class. Because then you'll just be able to download them.
Yeah.
Because I'm going to post it all online. Okay.
I was only asking because I want to make a binder for down there.
Oh, okay, perfect.
And I'll see, so that way if I'm not there, they can go straight to what we're looking for.
Okay, perfect.
Yeah. Shannon probably knows.
Yeah, show me. Oh. In what regard?
Yeah.
What's yours called? Like what?
TI-82? Oh, sorry.
It's TI 81.
Emily, what are you trying to type in?
No, I'm figuring.
You're figuring it out? Okay.
I was taking math course ever since I took yours, so I'm like trying to.
Yeah,
Get
you got to
myself
remind yourself a little
together.
bit. Yeah.
It's kind of cute, isn't it? Again. Yeah, I mean, it's so cute. It's cute. I'm gonna go in. Literally, we're filming us for 2 weeks.
Here you go, how the commands list.
Okay.
How the commands list. All the ones that give.
Well, it's okay. I'll figure it out, I know. I just need to get used to it again. Okay.
Cool.
Hmm?
Cool.
I always want to see something cool.
Some of my engineering courses I do graphic design, I do 3D models of this one.
So when you say you do 3D design, do you mean like 3D design in the 3D printer?
Yes.
Cool.
I have some pretty good ones. So the simulation. See how it expands? So the air, that is the air will be just blew up.
Oh, nice.
So we have to.
You can see how it deforms.
Yeah, because it's too much pressure. Yes.
Oh, wow.
Very cool. That was great, Edgar.
Look at that, I don't know.
Oh, there it is. It's open now.
Yeah. It's just a beast. Yeah. I mean, it doesn't have.
You said you're doing engineering, right? Yeah. You use some people? How that works? Oh, okay. I don't like that one. It's okay, but it is confusing because that was the first one I learned. All you gotta do is just picture in your mind and better. Most of it is just visualization, and then you just add the numbers. And
One thing that we lot of it acts like specific, like it's a 4-year-old.
oh yeah, that. But solvers that you do it way different. Like the big thing I see with solvers is the limitations. Like sometimes you sort like some things that the commands are just like solvers best. But if I had to compare the two, I think theirs has better limitations.
Okay.
I don't know.
Oh, that's interesting. Like
I know.
in the program, like there's
I'm not sure.
You were doing that. How is that? It's fun.
Yeah.
So it is.
no, it's just that you gotta like memorize the events. Like one of the times we had a program of any to give her the truth and give back the credit.
All right, folks. Let's have a seat. Keep going. So,
Think about what we did right now. This is a way better version of it.
okay, great. All right, Valeria, Hector, let's keep going. So everyone turn to page 1.2, relations, and let's do a quick review. It says, recall the slope-intercept form of an equation. What is the slope-intercept form of an equation? Of an equation of a line, by the way. What's the equation of a line? Yeah, y equals mx plus b. That's your classic formula for a line. What does the m represent? Slope. Yeah, m is the slope. All right, and then what did the b represent?
Remember the starting point?
It's called the, yeah, you can call it the starting point. It's the which intercept? Y-intercept. All right, very good. So what we have here is y equals mx plus b, where you have a slope and a y-intercept. Let's try one together real quick. It'll be a simple one. We'll do y equals 1 over 2x minus 3. So what does the 1/2 represent? The slope. And what does the -3 represent? Y-intercept. So I'm going to draw a quick graph here. And so I'm going to go down 1, 2, 3, and that's my starting point. The y-intercept is your starting point. And then I want to count out this slope. Now, we need to review how to even read a slope. The definition of slope, I'm going to put it here, m equals, a lot of people memorized it as rise over run. That's from your childhood. Rise is not a very good word because it implies you're always going up, which you're not. So instead, you could say vertical movement. Vertical is up or down. And then the word run, well, I don't really know which way run implies you're going, right or left, but it means horizontal movement. So vertical over horizontal is a slightly better definition. But the definition I always use, because it's fun to say, I define slope as the up-down over the right-left. And I always say it with an accent because it brings me joy. So slope is the up-down over the right-left. That is slope. It's how you move going up and down, right or left. And if you keep in mind on Descartes' coordinate grid here of your x and y axis, then for sure you know that up is positive, down is negative, right is positive, left is negative. And therefore, up is a positive number, down is a negative number, right is a positive number, left is a negative number. This right here is our definition of slope. So, how do I read 1/2? What does the top number mean, up or down? Up, up 1. What does the bottom number mean, right or left?
Right.
Right 2. So when you look at this slope, it reads up 1, right 2. So from my starting point, I'm going to go up 1, right 2, up 1, right 2, up 1, right 2, and so on. So that was a very fast review of linear equations, y equals mx plus b. So slope is the up-down over the right-left, and m represents slope, and that's how you read the fraction. And then your y-intercept is your starting point where you start the graph. We will certainly do more of this, but I'm just reactivating your brains because you probably all have seen this many times before in your childhood, your high school career, and so on. It's what? I didn't hear you.
I said it was traumatizing.
Traumatizing, yeah, right. So that's m and b. What do y and x represent? If m is slope and b is y-intercept, what's the x and y? Yeah, x and y are coordinates. They're coordinates. X and y is always a coordinate. So the x and the y are actually a coordinate that's on that line. So
the slope is going to be like a fraction?
Slope has to be a fraction because by definition, it's the up, down over the left, right. So yeah, it is a fraction. Slope is always a fraction. If it's not a fraction, you just put it over 1. Like if it was just 8, you put 8 over 1, and then it's a fraction. Okay, so x and y represent a coordinate. So for instance, what does that mean? I'm going to choose a coordinate that's on this line. So I'm going to choose this coordinate. I just found it. It's the coordinate 4, -1. I claim 4, -1 is on that line because I just drew it, and it looks like it is. So how do I check? Because the x and y represent a coordinate. So I'm going to take this formula, y equals 1/2 x minus 3. And I'm going to plug in the coordinate 4 and -1 for x and y. So for y is -1, x is 4. And now what should happen right now? When I'm all done calculating all this, what should I see? They should equal each other. So this is now -1 equals half of 4 is 2, 2 minus 3 is -1, and sure enough, -1 equals -1. We call that truth. Right? They're true. It's true that that's true. So any coordinate on this line, what will happen if I plug in the coordinate into this equation? It should be true. Now, who knows what it's going to be? It could be 5 equals 5, 8 equals 8, 10 equals 10, 13 equals 13. Who knows? The point is it's true. So if you take a coordinate from the line and plug it into the equation, it should give you something true. What if I take a coordinate not on the line? Like the coordinate 1, 1. Is the coordinate 1, 1 on the line? No. So what happens if I plug 1, 1 into this? Yeah, it's not going to be true. And if it's not true, what is it? You can say incorrect, or you can say false. 1 equals negative 2.5. Is that correct? That is false. So what can you say then? Every graph that you ever draw, every graph, the graph is shading. I just shaded all those points, just like on your interval. And shading means truth. They're all included in the solution set of this equation. And any point out here is false, lies, and sadness. There we go. So any point on the line makes the equation true. It's true. It's part of your solution set. Any point not on the line is false. It will not make your equation true. Now, this is philosophical, but it's very important because it'll run through everything we do. All right. We've covered that question. What does the m, b, y, and x all represent? M is slope, b is y-intercept, x and y are coordinates that are on the line that make the equation true. Now, just so you all know, like if you were on a first date and the other person's like, hey, tell me about y equals mx plus b, you should be able to give them like a 5-minute impromptu speech. Oh yeah, you got a pencil and paper? Let me tell you about y equals mx plus b. There's a lot to say. Use that on your next date. It'll go over really well. Okay, so give an example of each type of slope. So now, what are our slopes? Slope can be, what kind of slope is that? Yeah, positive. Slope can be negative. Slope can be 0. And slope can be undefined. Right. Let's pay special attention to this one, 0. That's a horizontal line. And this one is a vertical line. And now let's talk about those. So it says, give an example of each type of slope. There we go, we did it. Which is the what? That's a 0. Yeah, 0 slope. So you have a positive numbers, negative numbers, 0, and then undefined. And this is definitely all something you would need to memorize. You need to know right off the top of your head that if your line is going up, it's a positive slope. If the line's coming down, it's a negative slope. If the line is horizontal, that's 0 slope. And if the line is vertical, that's undefined slope. So this next part here says equations of horizontal and vertical lines. Because I already know how to do the equation of these two lines, I would just use y equals mx plus b. You can write this down directly below your examples. If I were to do y equals mx plus b for this one, what's one possible value for my slope? Positive 2/3. Sounds good. 2/3 x plus 1. So that's a positive sloping line. Give me a possible m value for a negative sloping line. Negative 2/5 x plus 2. Okay, so that's a possible equation for that line. That's a possible equation for that line. What's in my equation for this? So y equals mx plus b, but it's a horizontal line. So what's the slope? 0. What happens if you put 0 in for m? What's 0 times x? What's 0 times anything? 0. And what's 0 plus b? 0 plus b is b. Right? B plus nothing is still b. And what was b again? Y-intercept. So the equation of a horizontal line is y equals the y-intercept. That's the equation of a horizontal line. It's just y equals the y-intercept. So we just arrived that the equation for a horizontal line is y equals the y-intercept. So let's go ahead and do number 2 right there. Number 2, so we're moving down. Is it on the next page? It's just down below. It's just down below. So number 2 says y equals 3. Okay, that doesn't look like y equals mx plus b, does it? I mean, it kind of looks like it, but what are we missing? We're missing the mx, aren't we? And why are we missing the mx? Because n is equal to 0. So this automatically tells us this is a horizontal line. And we're all going to memorize that if you have y equals 3, that's really y equals the y-intercept. So how do we graph this then? Yeah, we'll just do a y-intercept of 3, and then we draw a horizontal. One thing to notice about our line, okay, it is horizontal, the slope is 0, the equation is y equals y-intercept. What do you notice about all the coordinates on that line? Like, look at this coordinate, that's the coordinate 0, 3. And look at this coordinate, that's the coordinate 4, 3. Look at this coordinate, that's the coordinate -5, 3. What do they all have in common? Yeah, but y is 3. That's literally what this equation is saying. Yeah, it's just saying the y value has to be 3. And in fact, one way you can interpret this equation right here is show me all the coordinates in the universe that have y equals 3. As in, the coordinate must look like this. And so where are all those coordinates going to be? They're all going to be right there. All of them. They're all going to be right there. And so what are we doing? We're shading all the coordinates that have a y value of 3. And what does that shaded picture look like? A horizontal line. Yeah, yeah.
Would we, for the white space, for the 2, 3, n?
Oh, you put x. That's the x value. Yeah, yeah. Okay. So that's a horizontal line you have to memorize. Y equals the y-intercept for a horizontal line. Now you're going to do something wonderful here. You're going to discover for yourself the equation of a vertical line. So listen very carefully as I say this. The equation of a horizontal line is y equals the y-intercept. So the equation of a vertical line is x equals the x-intercept. And just listen again. The equation of a horizontal line is y equals the y-intercept. So the equation of a vertical line is x equals the x-intercept. It's symmetrically just the opposite idea. So now if we look at number 1, we have this equation x equals -2. Well, we already knew that y equals the y-intercept was a horizontal line. So x equals the x-intercept is a vertical line. So now what do we graph? Here we got a -2 on the x-axis. There's my x-intercept. And then you just draw a vertical line. You know what we glossed right over is what even is a y-intercept and an x-intercept. We just plowed right into that, didn't we? What's that?
That's what it says.
It does say it?
Explain why it is.
Oh, yeah, we didn't even explain it, right? Well, so let's make sure we understand before I get too much further. If I have a graph, and let's just say that my graph looks like this, all right? This would be a y-intercept, and this would be an x-intercept, and this would also be an x-intercept. So in easy language, what's a y-intercept?
Point that's on the line.
Yeah, it's where the graph touches the y-axis. So it's just a point on the y-axis where the graph touches it. That's a y-intercept because the graph intercepts the y-axis. What's an x-intercept? It's a point on the x-axis that the graph touches. So those are x-intercepts. That's y-intercept. I should have said that right up front. I'm very sorry. So in this case, the x-intercept is -2. There's my x-intercept. I draw a vertical line. And again, what do we notice about all the coordinates?
It's the same thing with those other questions, but it's the opposite.
Yeah, so like here, this coordinate is -2, 0. This coordinate is -2, 3. This coordinate is -2, -1. What do all the coordinates on this line have in common? Yeah, the x value is always -2, and then the y value can be anything. So again, when we look at this equation, x equals -2, it's as if somebody is saying, show me all the coordinates that have x equals -2. And then you shading means truth. You're shading that whole thing. You're saying, hey, all those coordinates are true. They're part of my solution set. They are coordinates that have the x value of -2, and those points all lie on top of each other, and it looks like a vertical line. But what it is just the shading of all the coordinates in space that have an x value of -2. Okay, so now memorize it. A vertical line is x equals the x-intercept. A horizontal line is y equals the y-intercept. Now you'll notice we covered a lot of theory right there, didn't we? I mean, those are a lot of ideas, and you know, the good news is it's not like that's the first time you ever saw this in your life, but maybe it's been a while, and so it could still feel a little rusty. And so we practice. All right. Well, that's what we have for now. So again, a y-intercept is anywhere the graph touches the y-axis. X-intercepts are anywhere the graph touches the x-intercepts, or the x-axis. And that's how we graph a vertical line and a horizontal line. And so we're ready to go to the next section. Any questions or thoughts or feelings before we go to the next section? How's everyone feeling?
You be able to do one more?
Of the horizontal line and the vertical line? Well, sure. Here, I'll just put one on the board. What would the line x equals 5 look like? And what would the line y equals 3 look like? And while you think about that, I haven't shown you the website Desmos much. I haven't even showed it to you at all, right? Desmos? Okay, Desmos. This is the best graphing calculator in the world online. And so if I just type y equals 2, what do I get? A horizontal line that goes through 2. Actually, I'll do the examples I just showed you. So that's y equals 3 right there. So that was the extra example I just gave. Y equals 3. It's a horizontal line that goes through 3. What if I type in x equals 5? I get a vertical line that goes through the x-intercept of 5. So Desmos is very powerful. It'll graph anything you give it. Okay. Gabe, did that count?
Yeah, I really like the answer.
Oh, well, sure, yeah. Well, so in this case, x equals 5. Again, you have to memorize. This is really x equals the x-intercept, which is a vertical line. And so we draw a graph. The x-intercept is 5. 1, 2, 3, 4, 5 on the x-axis. And you draw a vertical line. Whereas y equals 3, this is y equals the y-intercept, which is a horizontal line. And so if I draw that, I go to the y-intercept of 1, 2, 3, and I draw a horizontal line. There are quite a few problems like this on more. So when you go to do your homework, they'll quiz you on horizontal and vertical lines. Okie doke. One thing I could have said at the very beginning is today is a day that's big on philosophy and deep understanding about what a graph even is. They've introduced the idea of the coordinate grid, which was made by Descartes, talking about coordinates, x, y, talking about x-intercepts, y-intercepts. So now we're going to get into graphs. So does everyone flip to this page? Graphs of equations. So let me show you the fundamental graphing principle. So up at the top, read it along with me. The graph of an equation is the set of points that satisfy the equation. Satisfy is an interesting word. Pizza satisfies, right? Pizza satisfies my hunger. When they say satisfy, they mean what? Make it true. So let's just do a quick little fun example here. I'm going to go over to Desmos, and I'm going to type in the equation x squared plus 3x minus 4. So the very first thing that we do when we talk about graphs is you can type anything in you want right here. You just start writing a formula. Do anything. You just start writing variables, numbers, and just type stuff in. And before you hit enter, you say, gosh, I wonder what that's going to look like. What would the graph look like for that? And then you hit enter, and you're like, oh, that's what it looks like. Right? So it's always a mystery. You type in any equation you want, and then you say, what does that look like? And then you look. You're like, oh, that's what that looks like. So this question, what does a graph look like, is actually very deep. what does a graph look like? Because if I type in something weird, like what if all of a sudden now I take my parabola, so I'm taking my parabola, and I'm going to take that and I'm going to divide it by x minus 1. No, not 1, 2. So now look at the graph. Would we have ever predicted that that's what that looks like? Okay, now watch, this is very subtle. What if I change that 2 to a 1? Well, all of a sudden, it just turned into a straight line. What if I turn that 1 into a 0? All of a sudden, it looks like that. And that is very different from that. Look at the difference it makes to change that 0 to a 2, to a 0, to a 1. What the heck? Right? So, folks, this is a very subtle thing. When you type in an equation, whatever equation you type, you should be asking the question, what does it look like? That's what it looks like. Now, what do we even mean? That's what it looks like. What is a graph? According to the fundamental property of graphing, the graph of an equation is the set of points that make the equation true. In fact, everyone circle the word satisfy and write make the equation true. So I'm going to go back to my parabola. Satisfy means make the equation true. So here's my parabola. And I'm going to find a point on it. It's not a very good parabola. That's okay. I'm going to do 6 and 9. There we go. I like that one. Or, is that? There we go. Everyone, can you all see what coordinate I just chose? Yeah, so that coordinate is on the graph. Do you all agree that that coordinate is on, wait, -2? -2, -17. Is that coordinate on the graph? Okay, now so everybody watch what that means. The picture of the graph, okay, where the graph shows up, what that means is every single coordinate on that line will make the equation true. So here's my equation, y equals x squared plus 6x minus 9. What was the coordinate? -2, -17. So if I take the coordinate -2, -17, what will happen if I plug in that for x and that for y? It's going to be what? Yeah, this is deep, deep, deep. So -17 equals -2 squared is 4. 6 times -2 is -12 minus 9. So now that gives us 4 minus 12 is -8 minus 9. And voila, -17 equals -17. The 17 doesn't matter. The fact that it's true matters. So this statement is true. And so every single coordinate on here, how many coordinates are on here? Infinitely many. All infinitely many coordinates that you can pick off this graph. If you plug it into the equation, what will happen? It'll be true. Okay? That's what it looks like. So when you say, what does an equation look like? It's the shape of truth for that equation. All the coordinates will make that equation true. So that's the fundamental graphing principle. And they're reminding us what an x-intercept and a y-intercept is. X-intercept is a point where the graph intersects the x-axis. Y-intercept is a point where the graph intersects the y-axis. And then they're going to tell us how to find the x and y intercepts. I'd like to not read that to you just yet. And instead, I'd like to walk you through the idea of how to find an x-intercept and a y-intercept. So you can just use the space over there on the right. Like you can use this space over here. And maybe we won't even do that example. Just use this space over here. And I'd like to talk to you about how to find an x-intercept and a y-intercept. So everyone draw a little graph. And just draw a little curvy line like that. And we're just going to call this thing our function. Now we've been saying y a lot, like y equals. You can also say f of x equals. Although we haven't reviewed functions yet, so maybe that's not entirely fair. Let me just go back over here. The example I just gave was y equals x squared plus 6x minus 9. You can also write f of x equals x squared plus 6x minus 9. Have you all seen this notation before of f of x? Maybe you have, maybe you haven't. So f of x is just an input-output machine. So right now, by calling it f of x instead of y, I can say, let's plug in 1. So f of 1 would be 1 squared plus 6 times 1 minus 9. And that would be 1 plus 6 minus 9, which is negative 2. So the 1 is my input, and the 2, negative 2, is my output. I just made that up. Yeah. So the point is you can use f of x to represent whatever equation you want. So let's call f of x. It's just going to represent whatever this equation is. And keep in mind that f of x and y are the same thing. So when we talk about a coordinate on this graph, any given coordinate you can either write as x comma y, or you can write it as x comma f of x. Because f of x means the same thing as y. It's, you're saying, hey, here's my equation. Okay, so we would like to find an x, sorry, let's do the y-intercept first. We'd like to find a y-intercept. This is our y-intercept. And let's just remind ourselves, what do all the coordinates on the y-axis have in common? Like this coordinate is the coordinate 0, 1. And that coordinate is the coordinate 0, 2. And that coordinate is the coordinate 0, 3. What do all coordinates on the y-axis have in common? X is equal to 0. And so, what happens if I let x equal to 0? That means I'm plugging 0 into the function. And that is in fact the truth, that the y-intercept will always be equal to f of 0. And what that means is just plug in 0. So if you just plug 0 into the equation, it's going to tell you the y-intercept. That's the definition. So you're all drawing this little picture right here somewhere so that we all know how to find the y-intercept. Y-intercept, any coordinate on the y-axis has to have 0 for the x value. And so if you plug 0 into the function, or if you just plug 0 in for x, that's going to tell you the y-intercept. Okay, what about the x-intercept? What do all these coordinates have in common? Any coordinate on the x-axis, like this coordinate would be 1, 0, this coordinate would be 2, 0, this coordinate would be 3, 0, this coordinate would be 4, 0. What do all coordinates on the x-axis have in common? Yeah, the y is equal to 0. And remember, y is actually f of x, both of which simply represent the equation. So if I want this value right here, which is my x-intercept, the x-intercept you will find by letting y equal 0. In other words, set f of x equal to 0. That means set equation equal to 0. And solve for x. This is a big idea right here that we're all just taking notes on right now. And what we just decided was that if you want the y-intercept, you just plug 0 into the function, into the equation. And if you want the x-intercept, you set the whole equation equal to 0, and then you have to do algebra and solve for x. Notice over here, if I just plug 0 into a function, like let's say I plug 0 in right now, what am I technically doing if I just plug in 0? What do we call this procedure where I say 0 times 0 plus 6 times 0 minus 9? What am I doing right now? I just did a bunch of arithmetic. It was pretty easy. Arithmetic, yeah, I simplified. Arithmetic is easy. So this process right here, this is the process of arithmetic, and it's easy. Whereas when I set an equation equal to 0, like let's say just for fun that my equation was 5x minus 20 equals 0, how do I solve for x? What would I do first to solve for x? Move the 20 over, so add 20 to both sides. Then I have 5x equals 20. And then divide by 5. Now what is this process called that I just did? What do you call that when you solve for x? Algebra. This process is algebra. And algebra is almost always, I don't want to say hard, but it's harder than arithmetic.
Compared to the longer process.
It's a longer process, exactly right. It's a longer process. So, we now have our tools at our disposal. This is perhaps the #1 tool that we're going to use all semester long. And so what we're going to do right now is go ahead and practice that tool. How to find the y-intercept, how to find the x-intercept. And right around now, I want to ask again, how are you doing? Are you feeling tired? Are you feeling hungry? Are you feeling sad? Are you feeling happy? Like, how's everything going? This is a lot of information. You know, it is a lot. I admit it's a lot. So, anyone want to say anything or ask any questions? Or yes, Omar.
Are we just in a graph?
Yep.
Wouldn't exhibit just put the origin at 9 on the y-axis and then just make the parabola face down?
Well, now that's absolutely true. So what Omar just pointed out for this parabola, in fact, let me just graph this one on the Desmos, is first of all, if it's an x squared term, what does the graph look like? All x squared graphs look like what? A parabola, a U shape. So negative x squared, automatically it's a parabola. And then the +9 bumps the y-intercept up to 9. So yeah, Omar's intuition was correct. This graph of negative x squared + 9 is simply an upside down parabola. And in fact, everybody, just take a look. Where's the y-intercept? The y-intercept is at 9. And where's the x-intercept? Yeah. So everybody, this is great. Let's use the graph, the Desmos for this one. Let's go ahead and now make our graph. Everyone go to that little graph right there. And let's label in the y-intercept is 9. So count up to 9. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, put your y-intercept at 9. And then go ahead and put your x-intercept at 3 and -3. So put those dots. Put a dot at 9, put a dot at 3, and put a dot at -3. And then just draw in your parabola. Just sketch it in. And in fact, that is often what we do. You find critical points like y-intercepts, x-intercepts, and then you just kind of sketch the rest of it. Yeah. So Omar, thanks. Was that your question? Yeah. Yep. And oftentimes, all you need is the x-intercepts and the y-intercepts. And if you know it's a parabola, you can just draw it in. Just one question. Yeah. Okay, so now let's turn the page. We're going to try this a few times. And when you turn the page, you'll notice that I've crossed out some of these equations and put in other ones. So I'd like you all to cross out those equations and put in other ones. We might just do these two for today, as opposed to all the rest of the other ones down below.
Because the other equation we did with +9 is the but basically upside down.
Yep. Okay, now both of these are also parabolas. X squared means parabola, so it's a U shape. X squared means parabola, so it's a U shape. The only difference is that this one I wrote -16 and that one I wrote +4. But the graphs will end up being quite different. So let's go ahead and do the first one. So everybody, we're doing, this is #1. #1, our function is x squared -16. And the instructions say find the x and y intercepts. Then it says create a table of values. Then it says sketch the graph. So let's start with finding the x and y intercepts. Now let's remember, which one is easier? Finding the y-intercept or the x-intercept? Y-intercepts. And therefore, let's start with the y-intercepts. You know, feel good about ourselves. You know, get something easy and done under our belt. So y-intercept. The y-intercept is equal to f of 0, which means just plug in 0. It never hurts to write this down over and over again, so it helps you memorize. So, what is f of 0 in this case? F of 0 is 0 squared -16, which is 0 -16, which is -16. So what is our y-intercept? -16. That shows kind of a silly number because -16 is like way down there. So just put a dot somewhere down there. That's your y-intercept. So put, you know, extend your y-axis down, put a spot, and put it at 16, -16.
You recommend
You can, but you can just put the dot as well. The dot is sufficient. Okay, so I'm going to keep running track of my work over here. Here's my graph, here's -16, here's my y-intercept. Okay. Now, was that easy? That's pretty easy. You just plug in 0. Okay, so now, x-intercept. To find the x-intercept, we said set f of x equal to 0 and solve for x. I honestly would write that down because you're telling your brain right now what the process is you're going to use for the rest of the semester. To find an x-intercept, you set f of x equals 0 and solve for x. What's f of x? X squared minus 16. So I'm going to go ahead and do it. I'm going to say f of x is x squared minus 16. I'm going to set that equal to 0. And that is the equation I'm about to solve. Okay. And when I'm done solving for it, what will I have found? The x-intercepts. So whatever it is we're about to find, those are the x-intercepts. So x squared minus 16 equals 0. How do I solve for x? X is being squared and subtracted by 16. So what do I do first? Yeah, add the 16 over. Now I have x squared equals 16. Now x is being squared, so we square root. And anytime you square root in the process of algebra, it's not just 4. The square root of 16 is 4. It's plus or minus 4. There's technically 2 answers. So when I write x-intercept equals 4, comma, -4. There were 2 x-intercepts. And so now I go onto my graph and I put on my x-intercept of 1, 2, 3, 4 and -4. And now that you've put your x-intercepts and your y-intercepts on your graph, then you see the U. You see the U shape, the parabola shape. Yeah, so it's already there waiting for us, and you can just take your pen. What wouldn't work?
I'm thinking negative.
Oh, okay. Yeah, so now just take your pen, make a U shape, and notice that we've just answered the question. If I went into Desmos and typed that in, I would ask the question, what does that look like? That's what it looks like. And what does every point on this graph do? Make the equation true. That rhymes. What does every coordinate on the graph do? Make the equation true. Okay, I'm sorry, that's terrible. That's terrible, but it's true. So there we go, that's number 1. We're going to try that one more time. We have number 2. So number 2, I'm going to wait a second just in case you're still making your nice little graphs. So, well, I mean, this is the process that the book shows, and it's the process that we use. How would you do it without doing all the steps? Mm-hmm. You mean the square root of 16? Yeah, in this particular case, that's true. You can just square root of 16. But you mean on the graphing calculator? Well, yes, you can just use a graphing calculator, and that's a good point. I'll show that. But just so you know, okay, so for this class, I'm going to collect this on the data test. And if it's blank, you get 0 points. So it's really important that you're writing down all the steps that we're writing down. They're really important now. You need to be taking notes. It's a requirement for the course. It's a requirement for the course that you're writing down everything I'm writing down. Especially the steps. You know, those were all the. So, like for instance, right here. Okay, good. You have part of that there. But you would need all that other stuff that I put up there too, all those notes, to know what the x-intercept and the y-intercept is. And then, yeah, the whole example that we just did is going to be a really good example for you for later on. So we're about to do another. We're about to do number 2. So, like I said, I scratched out these examples. Now we did x squared minus 16. And now we're about to do f of x equals x squared plus 2, or x squared plus 4. So do this whole problem with me. Onion. It's very important that you're writing down everything that I'm writing down. Because otherwise you're not going to get credit for the practice. And more importantly, you won't have the practice to pass the test. So if once you pass the class, pass all the tests, you need to be taking notes. It's your first day in class, so I'm trying to be as honest with you as possible. Okay? It's really important that you're taking these notes. So we're about to do the next problem. So write down everything I wrote down. Okay, Omar, did that all work?
Oh, yeah.
Okay, very nice. All right, folks, let's try the next one. We have f of x equals x squared plus 4. F of x equals x squared plus 4. All right, everybody, let's all come back together and try this out. The first thing we're going to do is find the y-intercept. How do we find the y-intercept? You just plug in 0. The y-intercept is literally equal to f of 0, which means you just plug in 0. So in this case, f of 0 is 0 squared plus 4. 0 squared is 0. 0 plus 4 is 4. The y-intercept is 4. So that's our y-intercept. It's just 4. So I'm going to start my graph. Here's my y-intercept. 1, 2, 3, 4. It's 4. Now, how about the x-intercepts? X-intercepts, to find an x-intercept, what do? We set the function equal to 0, set the equation equal to 0, and solve for x. So I'm going to set f of x equals x squared plus 4 equal to 0. And that's what we need to solve, is x squared plus 4 equals 0. So how do we begin solving? Subtract the 4, move the 4 over. Now we have x squared equals negative 4. X is being squared, so you square root, but uh-oh, what's the square root of a negative number? It's undefined. Therefore, what do we know about our x-intercepts? Where are the x-intercepts? There aren't any. There aren't any. The graph does not intercept the x-axis at all, which makes sense because this is a parabola that's facing up. The parabola is here. Does it touch the x-axis? Doesn't touch the x-axis. So you just say, there are none. There are no x-intercepts.
Could you
So how do you call that?
How do you draw it?
How do you call it? I mean, since it doesn't touch the.
Oh, how do you draw it? What do you mean? How do you
No,
call it?
I mean, does it have a name or something?
It's just
Like,
parabola.
just a problem. Yeah. Positive.
No.
It doesn't have a name.
No.
It's just several.
That's just parabola.
Well, the first thing you would want to look at is the slope.
Okay.
The first thing you want to look at is the slope. The slope is going to tell you whether or not the parabola goes up or downward.
You mean the sign in front of the x squared?
Yes.
Yeah, so it's a positive x squared, so it's facing up. X squared is facing down. But yeah, in this particular case, we're done with this problem. Yep. Now, there's one thing that we didn't do for either of these yet. We just found the x and y intercept. We didn't do part B, which is create a table of values. So let's make a table of values for this one, because it will help us draw it. Because you'll notice, is my drawing very accurate? Yeah, so let's find out. So how do we find out? What we're going to do is make a table of values here. A table of values, you have your x input, and then your function to calculate your output, which is x squared plus 4. So when we make a table of values, we need to choose some values to plug in for x. What value should we plug in for x? Well, I know that my graph is here. And I already know what plugging in 0 does. So we might as well try 1 and 2, and -1 and -2. Because that way we can see what's happening to the right and left of the base of the parabola there. So we're going to plug in the numbers 2, 1, -1, and 2. How did I choose those numbers? They're small. They're to the left and they're to the left. I'm sorry, they're to the right and to the left. And they're going to give me some indication of how wide the parabola is so that I can make a good graph. So what we're going to do now is plug these numbers into this function. And just like before, you're going to take your function and write it empty. So x squared plus 4, I'm going to write as something squared plus 4. Something squared plus 4. Something squared plus 4. Something squared plus 4. And then I just go through and I plug in my inputs. This is what a function is. A function is an input-output machine. So I input 2, I input 1, I input -1, I input -2. And I do all those calculations. So everybody's making a table of values? So this first one, 2 squared is 4, 4 plus 4 is 8. 1 squared is 1, 1 plus 4 is 5. -1 squared. What's -1 times -1? Positive 1, so 1 plus 4 is still 5. And then -2 squared, that's -2 times -2. Yeah, negative times negative is still positive, so that's 4 plus 4 is 8. So what I want you to notice here, folks, is that when you have an input-output, what is that really? What is an input-output on your graph? They're all coordinates. Input-output is a coordinate. In fact, one thing that you can do when you talk about a coordinate on a graph, there's 3 different ways that you can say it. A coordinate on a graph is either x comma y, or you can call it x comma f of x, or you can call it in, out. Very important. Every time you do an input and an output, that's actually just a coordinate. So what are the coordinates that we just found? 2, 8, 1, 5, -1, 5, and -2, 8. Anytime you make a table of values, it's really a list of coordinates. So now we can make a really good graph. Because now I'm not just arbitrarily drawing some U shape. 1, 2, 3, 4, 5, 6, 7, 8. Now I'm actually knowing how wide this parabola is. So now I can put in the coordinate 1, 5, 2, 8, -1, 5, and -2, 8. And now I've got a good connect the dots scenario where I can connect those dots and I know very accurately that's what my parabola looks like, as opposed to just some sloppy sketch that you make too wide or too skinny.
Are you want us to do that too?
Absolutely. Yeah, this what we just did is a core skill that we'll work on. This is the first time we'll do it. We'll practice it more. Yeah.
So for the exams, you want us to draw the table as the work?
Many problems on your test will say make a table of values with at least 3 values and then sketch a graph. Yeah. Okay, so does everyone have a graph now? You drew in your graph on the coordinate grid? Yeah, take a moment, draw in your graph. Oh yeah, that is the graph, and that is what it looks like. We're not going to do those two. We can cross them out, but that is what it looks like. Yeah, that's good. You can cross them all out.
That way you do drop on to like, erase it.
Is there anything else close on that? Yeah, no.
All right, so everybody, you can cross out number 3 and 4. We're not going to do those right now.
Right now or?
Ever. You can cross out. We won't do those.
I usually sharpen my hand.
I'm not going to do it now or ever.
Good question.
And so when you cross those out, that means I'm not going to grade that when I collect it. Because I'm collecting these packets from you on the day of the test to give you a grade. But if you cross it out, I'm not going to grade that. I'm kind of against it. So we just have a few minutes left. And I want to remember to let Lee talk at the end. So let's go ahead and just glance at section 1.3 so we can put some ideas in your head so that it will marinate in your brain. And when you come back on Wednesday, you'll be ready to think more about it. Right? Because we don't have school on Monday. So it's Monday or Wednesday, we're coming back. So let's write down all the way up at the top there. What is a function?
Oh, great.
Yeah, function.
No, I have a physics class after you on Wednesday.
Oh,
Before you know.
the function is, okay, so a function is, we write it down as f of x. Right? So that's a function, f of x. And what a function is, such as f of x is an input-output machine. Oops, input-output machine. And what that means is you start with some sort of formula. You can just put this in the margin. Say you have f of x equals 2x plus 5. So f of x is the idea of a function. F stands for function, and x is where you're inputting numbers. And over here you have some formula. So essentially you can input anything you want. So what if I inputted 3? Then that would be 2 times 3 plus 5. 2 times 3 is 6. 6 plus 5 is 11. This is my input. This is my output. That's fundamentally what a function does. Is you plug in a number and you say, what will the output be? And then you see what the output is. Together, the input and the output together are a what? Coordinate. So a function is an input-output machine. And what it's creating through this input-output process is coordinates. And those coordinates show up on a graph. And then you look at the graph and you say, oh, that's what that looks like. So that's your function. It's an input-output machine. Now, as you can tell here, if I type in a few other numbers like 5, if I input 5, and that's 2 times 5 plus 5, 2 times 5 is 10, 5 is 15. So if I input 5, I get 15, and my coordinate is 5. This is what a function is. Now, it's one thing to say a function is any input-output machine, and that's true. A function is just an input-output machine. But in mathematics and in physics and chemistry and biology, we like to work with well-behaved functions. And a well-behaved function means that if I plug in 5 today, it should equal 15. And if I plug in 5 tomorrow, what should it equal? It better still equal 15. Right? I mean, we're just doing arithmetic. And there's only one answer to an arithmetic problem. There's not like lots of different problems to an answer to an arithmetic problem. So if tomorrow I plug in 5 and I got 13, that would be a problem. What would that tell you if tomorrow I plugged in 5 and I got 13? That would mean that I made a mistake, right? Yeah, I must have made a mistake because there's no way that 2 times 5 plus 5 is somehow equal to 13. So one thing you know for sure is that for each input you plug in, there can only be one answer. And if 2 different people got 2 different answers, what would that tell you about one of them? One of them got the wrong answer. Maybe they both got the wrong answer, honestly. But at least one of them had the wrong answer because arithmetic only gives one answer. So the very first thing that we'll note is the next definition there. It says a function is a relation in which each x coordinate is matched with only one y coordinate. That's what we call a well-behaved function. So from now on, when we use the word function, let's write this down with me here, also in margin. A function means each x input has exactly one y output. What time's class on? Oh, 250. Oh, I have still 50 minutes. This is great. Okay, so that's what we mean by function. To be fair, the word function is used in 2 different ways. A function, on the one hand, is any equation you write down. If you write down an equation, you can graph it. You can look and see what it looks like. But when we use the word function, we normally mean that each x input has exactly one y output. Now, what does that mean? If each x input has exactly one y output, that's a well-behaved function. What if it didn't? What would that look like? Again, what if I plugged in 5 and got 13? That would mean that I have these 2 coordinates. Well, now what do those coordinates look like? If I have those 2 coordinates, 5 and 15, well, they won't intersect. But let's look. So there's 5, 15. And then 5, 13 would be here. What do you notice about those 2 coordinates? They're stacked right on top of each other. Okay? That's what we're not allowed to have happen when we deal with well-behaved functions. You're never allowed to have 2 points stacked right on top of each other. Because that implies you plugged in 5 one day to calculate 15, and plugged in 5 another day to calculate 13. That can't happen. So you can never have 2 points stacked on top of another in a well-behaved function. So that said, take a look at the vertical line test. If a vertical line intersects a graph in more than 1 point, then the graph is not a function. So that's called the vertical line test. The vertical line test means that if I hold up a vertical line, it better only touch the graph at 1 spot. So just take a look. If I put my line vertically here, how many spots am I touching the graph? Just 1. How about here? Just 1. How about here? Just 1. This is a function. But this is not a function. Because if I put my vertical line here, how many times does it touch the graph? Twice. That's no good. That's not a well-behaved function. So this is not a function according to our definition. This is a function. What about here? If I put my vertical line here, it's only touching that point. Only touching that point. Only touching that point. Oops. Now it's touching 2 points. This is not a function. So go ahead and write no, yes, no.
That makes it whole entire
Right, it makes the whole thing not a function. Yeah. And let's just keep going. Just flip the page real quick and let's compare the rest of these. How about number 10? Is that a function? Every vertical line that you look at, does it only touch it once? Yeah, this is a function. Oh, number 10. The 10 is a function, you might guess. How about 11? Every vertical line that you draw or can imagine, will it only touch the function once? Yeah, that's a function. How about here? Will every vertical line only touch the graph at most once? Well, where are you saying no to?
Oh, yeah.
This one?
Yeah.
Well, how many times does it touch an actual coordinate? Just once, because that's an open hole. An open hole is nothing at all. There's no coordinate there. So it passes there, and every other vertical line only touches it once. So yes, this is a function. It's a weird-looking function. It has a hole in it. It has a gap in it, but it's still a function. It's still a well enough behaved function that we call it a function. How about this one? Is this a function? Does every vertical line only touch it once? Yeah. It has a big old gap in it, but that's fine, so long as the vertical line only touches it once. What? Yeah, that'd be missing data. This one, is that a function? Every vertical line only touches it once? Yeah. Function? Yeah. So all of those are functions. Even though they look different, weird, they're very different, they're still functions in the way mathematicians refer to functions. And the reason we have this, definition is because real-world applications like physics and chemistry and biology, any function you find in there is going to be a function. Because, like, if you did a physical experiment, you can't have 2 different things happening. Like, if I take my pen and I drop it, it's going to fall. If I took my pen and then it went up, that'd be really weird. Like, you can't have 2 different outputs from one input. Well, that's a much longer question than real quick. But let's just think about this for a second. I have 4 minutes left. We said what a function is. We talked about the vertical line test. And yes, let's introduce the idea of domain. Let me just check here, because I don't want to rush anything. Yeah, we do have some minutes left. Okay, let's look at that definition, domain and range. What does it say the definition of domain is?
All x values.
Yeah, all possible inputs. Everybody underline that part in particular. All possible inputs. So that's the domain. We're creating a set of all the numbers that you can plug into a function. So for most functions, you can plug in any number you like. Like look at f of x equals 3x. Can I plug in any number I want? Can I multiply any number by 3? Well, your calculator will give you an answer. You can take any number, multiply by 3, your calculator will give you an answer. What about this function? F of x equals the square root of x. Can I plug in any number I want?
Yeah, but you want to
Well, right, if I did the square root of 5, it'd be like 1.2, lots of decimals. But can I plug in a negative number? No. So a negative number is not a possible input. So that's what we mean when we talk about domain. Domain is, what numbers can I plug in? In this case, everything. What numbers can't I plug in? In this case, I cannot plug in any negative numbers. So that's what we mean by the word possible. It's not possible to plug a negative number into this. What happens if you do the square root of a negative number on your calculator? You get an error message. That's the definition of domain. The main means, what are all the possible inputs that I can type into my calculator and my calculator will give me an answer? Versus, what are the inputs that my calculator would say error? And what we do is we put all the possible inputs together in interval notation and say, these are all the numbers you're allowed to plug into the function. Range works the same way. Range is what? All possible outputs. Yeah, for y values, but outputs is a key word there, so all possible outputs. So for instance, again, with the f of x equals 3x, can I make that equal anything I want? Like for instance, can I make that equal to 30? What would I have to plug in for x to make that thing equal 30? Plug in 10. Can I make it equal negative 30? What would I have to plug in? Negative 10. I can make this thing equal anything I want. You tell me a number, I can find the x value to plug into that to make it equal. So in this case, the range is everything. All real numbers. I can make 3x equal anything in the universe if I choose the right x value to plug in. But now consider f of x equals x squared. Can I make x squared equal to anything in the universe? What happens if I plug a positive number into this? A positive times a positive is positive. What happens if I plug a negative into this? A negative times a negative is still positive. Can I make this thing equal something negative? No. Negative numbers are not a possible output. So when we talk about the range, all possible outputs, some outputs are not possible for some functions. So in the case of the function x squared, the only possible outputs are positive numbers and 0, but not negative numbers. Okay, so that's the concept. That's the main concept. When we talk about domain, we're talking about what numbers can I plug in that my calculator will give me an answer as opposed to an error message. And the range is, what are all the outputs that I can get out? Because sometimes there are outputs that won't come out of a certain function. So how does that sound for, this is the definition. Hector, we didn't get to actually doing a problem, but that's the idea. And so now your brain will think about that. And so what are your expectations? Well, we just started 1.3. That's definitely not your homework, and it's not due on Monday. So what is due on Monday? So due Monday is only on more. You have to do sections 1.1 and 1.2. That's it. Those are the only sections you have to do due Monday. I'll push the due date of 1.3 a whole week back. Because due dates are only ever on Monday. So the only thing you have to do this Monday is 1.1 and 1.2. The next week, 1.3 will be due on Monday. Okay, so we're going to leave here now. You all go home. You're going to try your homework on more. We don't have school Monday. You'll come back Wednesday, and we'll pick up from there. Did everyone give me their syllabus quiz and their personal information? If you did not, please bring it up. I think everybody did. And that's it, folks. I want to compliment you. This was hard work today. I don't doubt it. This is hard work. These concepts are tricky. It's challenging. Maybe it's been a while since you've done math. This is tough stuff. So I really encourage you to email me. Even if you have nothing to say, email me anyway. Just say hi. But email me and ask me your questions because I'm here to help you. We want to help you right up front, not like wait 3 weeks. Because 3-4 weeks in, if you're feeling lost, it's too late. Okay, now Lee.
I have nothing to say. I have to be like, I have to be.
Well, that's fine. Okay, so Lee has some important information for you real quick.
Okay. So has everyone seen the schedule that Mr.
I posted it on the
posted
Canvas.
before? Okay. So here's the thing. I want to make sure that I'm available to you guys when you guys need me, or at least the best I possibly can. So I have the schedule here. What I would like for you guys to do is go and circle the times that you believe is best, and then if the time is not on there, go and put it on there. So if I can make it happen for you guys, I'm going to do everything I can to be there for you.
Thank you.
Yeah, so in other words, circle the times you can actually go. Like work is not in the way. You don't have to pick up your kids. You could go. Circle those times.
Now, if you guys need like more like a personal time, like a one-on-one time, all you gotta do is let them know up front. Let them know that you're in the 150, 120 class with Mr. G, and they should be able to take care of everything for you from there as well. Yes. You don't have to.
Thank you, folks, for filling that out for Lee. It's wonderful that Lee is being so flexible.
Is it, can you put multiple things or one?
Like for you, like if you were
Yeah.
that, you can ask for anytime you want. Whether or not I can do that